So the first of our short papers will be the deductive reasoning with incomplete knowledge via repeated analogies. Did it pick up? Oh, it didn't pick up.
I'll introduce myself anyways,
Okay.
but thank you, Ben.
Thank you.
Yes, so I am Willie Wilson, and I'm presenting my work with my student, Lissangel Martinez, as well as Irina, Rabkina. And this is on deductive reasoning with incomplete knowledge via repeated analogies. So what are the goals and motivation of this? Effectively, we want to do basic logical deductions, but we'll also be able to handle cases where we are missing some knowledge, where some knowledge is perhaps incomplete. And use the same reasoning process, whether we're dealing with complete knowledge or incomplete knowledge. And this is based on some of our prior work using repeated analogies for goal recognition. So we took an algorithm that we had previously, made a couple of small tweaks to this, and now have applied it to logic deduction. So as a quick overview of what this model is, what this algorithm is, so we call it RAGER, repeated analogies for goal reasoning. And this is a forward chaining algorithm. So we start off with gamma, which is our set of available facts. We also have over here our model library. And so it's going to look in the model library and find one of the models that matches with the available facts. Once it finds a match, it's going to apply the model and create a new gamma, and this new gamma is going to replace some of the facts in the old gamma and add in some new ones. And of course, now this process is going to repeat. Again, it's going to now use this new gamma, match with the models in the library, and continue to find new facts, infer new facts. And this will continue to until we are not able to infer any new facts, or until one of these gamma that we have has the goal that we're looking for. So this is goal directed. All the matches that we're doing are actually done via analogy. So thank you, Joe, for giving a quick introduction to analogy this morning. So how is this working? So we have an analogy that I'm showing right here through graphical means. The rest of this is going to be using predicate calculus. But we have two cases here, and we can see that when using SME, that these two cases align. And then SME also is going to help us find some candidate inferences based upon this alignment. In addition to SME, we're also using Macvac, which is a tool for doing analogical memory retrieval. And so Macvac is going to have the model library and is then going to quickly look over the model library to find up to 3 possible models that we're then going to use when doing our SME comparison for analogy. So to show how we're using analogy to do logic deduction, I'm going to walk through a small example just using Block's world. So we start off with 2 facts in gamma. This is that A is on B and B is on C. We have one model, this horn clause, saying that if X is on Y, Y is on Z, then of course X is above Z. And we're going to re-represent this not as a horn clause, but with these 2 statements saying that the consequent X above Z has the antecedent X is on Y and the other one. And so when we take this gamma and we take this model and we pass them to SME to find some alignment between these, we find that many of the terms align. In particular, we have things like the is on aligns with the is on. We have that B aligns with X, and we have, or A aligns with X and B aligns with Y, so on and so forth. So we have all of these alignments. And from all these alignments, we then are able to see that since a couple of the terms in the consequent also align, that then allows us to make a candidate inference. And this candidate inference is then that A is above C. So at this point, we have, in a sense, mimicked the process of forward chaining with deductive reasoning. One thing that's a little different than our typical forward chaining, instead of adding this new fact to gamma, we are actually going to replace it. So we are going to take the facts that were used that aligned with one of the antecedents, and we're going to swap those out and put in the consequent. This is a small limitation that we're currently having. This has worked in a lot of the problems that we've explored so far, but we are also going to look at perhaps relaxing this constraint and just doing our typical thing of adding the fact to gamma. So now what we want to do is, now that we have this basic process working with complete knowledge, we want to take this exact same process and now apply it with incomplete knowledge without any changes to the algorithm. And we're able to do that because, again, the way that the matching is working is using analogy. An analogy is not going to require a perfect match between the antecedents and the available facts. And so if there is some good analogy between the available facts and some model, then we're going to be able to apply that model or apply that rule. For this, I'm going to shift briefly to an example from chemistry. And so we want to be able to infer one of 5 things: that some element is a metal, a negative metal, a non-metal, negative non-metal, or a noble gas. In particular, we're going to look at just silicon. We start off with these 3 facts about silicon. Now, our model library has 14 models to be able to infer whether an element is positive, negative, or neutral, and whether it is metal or a non-metal. And so when starting with this gamma and starting with these 14 models, we run Rager on this, and we find that we're able to, so the top here is our initial gamma. Our next gamma then is the result of inferring that it is a negative element. And then after one more inference step, we then finally infer that silicon is in fact a negative metal. Now, of course, this is running with complete knowledge. And so now to demonstrate a little bit of how the incomplete knowledge works, we're going to take away this one fact and see what is now going to happen when we remove this one fact. And so at the top, we have the gamma now missing that one fact. The first inference step is still the same. It still infers that it's a negative metal. But at this point, since it doesn't have the state of matter, it can't necessarily guarantee that it's going to be a negative metal. And so it makes 2 possible inferences, one based upon whether silicon is believed to be a solid, and the other based upon whether silicon is believed to be a gas. And so it makes these 2 possible inferences based on 2 different models. And I think one thing that's really interesting here is effectively what's happening is that it is assuming, given incomplete knowledge, it's either going to assume that silicon is a solid, or it's going to assume that silicon is a gas. But it makes both of these inferences. Since this is goal-directed, we also want this to be a heuristic search, so we do a best first search. The heuristic that we're using is that the similarity score. So Joe briefly introduced the similarity score this morning. So the similarity between the fact here in the purple and the model, and what is the analogical similarity between those. So the similarity score that SME gives might be a small number. In this case, it actually ends up being the same number because there's going to be about the same amount of alignment between the model and the initial facts. In larger cases, it's not always the same similarity score, and so we use that similarity score to drive the reasoning. So one thing I also found really interesting is what is the role of Macvac in this? Because for everything that I've talked about so far, really is just based upon SME and how SME does the matching. But we are using Macvac to be able to find up to 3 models from the model library. And once it finds up to 3 models that are going to be likely to be similar, it will then do SME on each of those 3 models. In most cases, it's only been retrieving 1. That is a very common outcome. But it will retrieve up to 3 cases. So to explore really what is the role of Macvac in this, we did a very, very small experiment. And we looked at what if we don't use Macvac? What if we run SME on every model in the library? And so for the example that we have 14 models in the library. And so we would do an SME comparison between the available facts and all 14 models. What is the analogy that gets drawn, and can we then apply those models to infer something new? And so we expect there's going to be a trade-off here. There's going to be a speed improvement by using Macvac, since it's going to get no more than 3 models. But we figure that there's also going to be a possibility that running without Macvac is going to be more accurate, because there's a risk that Macvac is going to filter out some of the relevant models. So in this quick little experiment, we ran with and without Macvac. The without Macvac means we run SME on everything in the model library. We tried this both goal-directed and exhaustive, meaning are we able to infer some goal, and once we are able to infer that goal, we stop, or we run it exhaustively, meaning we run it until we can't infer anything new. For all this, we are using a complete knowledge case, and so we're running with the 3 facts related to silicon. So first, we did confirm, as expected, Macvac is going to indeed be significantly faster. When we are running it either with no goal, in which case we're running it exhaustively, or whether we're doing it goal-directed, it's going to come up with exactly 4 nodes in our inference tree, or inference graph rather. If we run it exhaustively, well, we actually stopped it at 1,500 nodes. So our inference graph ends up coming up with 1,500, or over 1,500 nodes. Once we hit 1,500, we figured, well, that's enough evidence for us, and we called it quits at that point. So it is indeed significantly faster, and not to mention, not only is it's producing fewer nodes, but it also means it's making fewer calls to SME. What we also found interesting, and this is a very small case, I'm not going to make any generalizations from this one example, but in this one example, we did find it was indeed actually more accurate to use Macvac. And this was a really surprising result. And so this is because when we were running without Macvac, it was able to do matches with most of the models. So in our first case of those 3 facts, we were able to then match with 11 of the models. And 11 of those models, or sorry, 10 of those 11 models probably should not have been ones that we were trying to match with. So we're making a lot of matches with models or matches with rules that are not actually good matches. And this comes up for a couple of different reasons. One is because we're using analogy and we're allowing for partial matches, we're now partially matching with rules that are perhaps inconsistent with some of the facts that we have. And some of this inconsistency comes from being able to map constants to other constants of different type. And I'm going to give you an example of that right here. Because what we started to see is that Macvac was starting to give us a partial unification. It's definitely not doing full unification, but we saw it doing some partial unification. So in traditional unification, we might want to align these 2 expressions, have one unify with the other. And when we have running with Macvac, we similarly are going to have these 2 expressions align. And what's interesting here is that silicon and X are aligning. It does, SME does not know anything about X, does not know that I'm treating X as a variable. It is just another entity. Since it is just another entity, that also means that these 2 expressions will also align. And so thus we can say that silicon, silicon is a solid and silicon is a gas. Both of these can align. This is actually a desirable thing when using SME typically, but this is not going to be a desirable outcome when doing logic deductions. So this is one of the big reasons why when we run without Macvac, that we get a lot more inferences and a lot more undesirable inferences, including many inaccurate ones. So what are my next steps? So next steps, we have some very basic heuristics right now. As I said, we're using the similarity score. Found that the similarity score really is insufficient. I think 2 things that we need to improve on. Since we're trying to do a goal-directed search, we need to have the goal actually in mind on the heuristic. But also we need to have the assumptions also integrated into the heuristic so that we're minimizing the number of assumptions that we're making at each step. Speaking of assumptions, I think there's a lot more work to do on the assumptions. Right now, Rager is making implicit assumptions. So it implicitly assumes either silicon is a gas or implicitly assumes that silicon is a solid. We want to make those assumptions explicit, and by making them explicit, we can track the assumptions and ensure some sort of consistency. Also, as the example I showed on the previous slide, where we are able to align gas with solid, we want to be able to constrain that. So we want to be able to add some SME constraints so that variables can map to any constant, but constants generally are going to have to map with the same constant. Lastly, what I want to explore is see if I can prove that this is a sound algorithm when there's no assumptions. So of course, we won't be able to show that when we have incomplete knowledge that it's always going to be sound, but I want to show that when the algorithm is making no assumptions, that it is in fact sound. And I think we'll be able to prove that. So just to wrap up, I'm using a deductive reasoning via repeated analogy, and the same algorithm is being used for both complete knowledge and incomplete knowledge. And it's interesting to see the role that Macvac plays in doing some partial unification. And thank you.
So Macvac is a two-stage retrieval. So you couldn't you just use Mac, the minier called part, to reduce the amount that increase the amount that's chosen? So Mac is going to retrieve up to 3 models, but it doesn't do any alignment. So I need that alignment to do basically the other half of unification of being able to say that X can be substituted with silicon. So I still need to do, the second half of Macvac is SME. And so I still need to do the SME part. And SME is actually the most critical part.
I'm not sure if my question has already been answered, but I was wondering about the SME part. So SME specifically aligns the structure, but not the actual content, not the actual word, whatever being
So
used.
it will not only align the relations, it will also align the entities as well. It's just that the relations have to map to the same type, but the objects, the entities don't have to map to the same type. And that's why ISA has to map to ISA, but the solid can map to gas.
So I think you're really doing abduction rather than deduction, but structurally I understand. But it's important because there's a long line of work on abductive reasoning that feels very similar to this, and going back to Hobbes and Mooney, right? But I've been working on this for a while, and other people recently, Andrew Gordon at ICT, right? So the issue there is that either you have to do sort of extensive search, like he does best first search and considers a bunch of things, or in our case, we do greedy search, but we get stuck at local optima if the explanation, the proof involves long distance relationships. And my question is there something about your approach that lets you, I mean, I can't tell whether you were doing, it didn't look like you were doing extensive search, are you not looking at problems that require long distance relationships, or is there something about the larger scale structure of your models that is letting you get at that?
What do you mean by the longer distance relationships?
Well, so for example, you have you're doing data directed inference, right? Not goal directed. So it's forward chaining, you said, right? And we are too. So if there's trying to find a proof tree, and you've got some things down here, but there's a bunch of stuff in the middle that's missing, and so you can't find the direct connection. If you had all this stuff down here, it'd be easy, but you have to find like a long path between things. If you had a large scale schema, I can imagine that would help with that, but it didn't. I couldn't tell what your models were like. Is that what's going on, or are you not looking at problems that require that yet?
I think right now, I think we haven't looked at models that really require that yet.
Okay.
I think that's not the scale at which we're looking at yet. I think
fine.
one of the next things to do is to scale this up and look at more complex problems.
Well, I do think that SME has the potential, but you have to give it the right structures. Let's talk about it later.
Yeah, you absolutely need the right structures. And I think that's also why I want to look at getting the right heuristics as well, because the heuristics I have right now are just on the smaller problems I've seen, that the heuristics are going to get it to go down the wrong path.
I thought SME had wonderful heuristics. They're not good
Oh,
enough?
SME has great heuristics, but the SME heuristics for this are not going to answer the bigger problem. Constantine?
I was just wondering if you had any thoughts on maybe learning models, given the close connection between Macvac and Sage.
Yes, I have in fact thought about this, including, so my collaborator, as you know, Irina Rabkina, she has her analogical theory of mind, where she is essentially learning some models. And so we have a very short paper at the AAAI symposium last year that looks at how can we combine Rager with Atom, so we have some learned models and some a priori models, and how can we kind of put those two together. This still hasn't quite worked out as well as we want, but we're definitely looking at how we can learn some of these models.
Okay, thanks. As the next talk wants to get ready, there's a couple questions from Slack. But I guess one of them, I'm gonna sort of paraphrase, sorry for Slack, but do the goals act as implicit or explicit constraints on retrieval when you use these?
The goals are, I really like that question. The goals currently are not included in the Macvac retrieval at all. I'm actually making relatively poor use of the goals currently. The only way the goal is really being used is to tell the algorithm when to stop, but they're not being used to direct the reasoning in any way.
Thank you. Let's thank our speaker.